Okay, third and maybe final, it might take two actually, videos of the videos on the DHSS model, and this is standard original 1974 DHSS model in its simplest form. It's a limited resource, costless to extract. Okay, and for pedagogical reasons I left this from the previous one. But now, there's no need for inputs. And R is just the choice variable. You just choose how much R. The owners of this resource just choose how much R to supply to the market, but there's no need for any inputs. So we can get rid of the X here as well, which I forgot previously. So I don't need to worry about it now. And we can get rid of it here too. I'll use my finger here, it's a bit easier. Okie doke. So I think this is a fair... Oops, no. I is SY. I think that's just looking good. Yeah. So, this is the DHSS model. How are things going to pan out? Let's see. So for the time being, we're told, slide 5, assume a social planner who releases a resource flow, R, which declines over time at some exogenously given rate, theta. It declines at rate theta. So we're told that minus R dot over R equals theta. Or if you like, R dot over R is minus theta. Because R dot over R is negative, yeah, it's declining at rate theta. And then we're told to solve for BGP. Okay, and again I'm going to do it super quick and hopefully I won't screw up this time. Okay, so BGP, therefore, K dot over K, constant, but K dot over K is S, Y over K minus delta, therefore, Y dot over Y equals K dot over K. But Y dot over Y is, and now we've got L is constant, K is a variable, AL is growing at G, R is shrinking at theta. So Y dot over Y is 1 minus alpha minus beta, G plus alpha, K dot over K, plus beta R dot over R, which is minus beta times theta. Okay, and the other terms that could have cropped up, like with L dots in them, for instance, are 0. Okie doke. And now K dot over K we know K dot over K equals Y dot over Y, so 1 minus alpha, Y dot over Y equals this, Y dot over Y is this over 1 minus alpha minus this over 1 minus alpha. And this over 1 minus alpha is 1 minus beta over 1 minus alpha. G, that one we shifted over and then divided, so that's gone. And minus beta over 1 minus alpha theta. Okay, so you can do this super quick if you know what you're doing. It's not that hard. If theta happened to be equal to minus g, which means that resource extraction is increasing at rate g, we're back with solid, aren't we? Because then this is plus beta over 1 minus alpha g. So then we have y dot over y is g. But we're told that theta is actually declining, so then this puts a big brake on growth. The growth rate is going to be this was with land, isn't it? If we set theta equal to naught, then r dot over r is constant. That's like the case with land, and surprise, surprise, we get the land result back. But if theta is bigger than 0, resource extraction is actually declining. That pulls growth down even more. Okay. Solve for growth rates on the BGP. What can we say about the initial rate of resource consumption? Okay, so I'm actually now going to solve. I've solved for y dot over y. I'm actually this time going to solve for the prices as well. Okay, so pi is pyy minus wll minus wkk minus wrr. Okay? So the first order conditions are d pi, right, so the representative factory owner is thinking, how many people shall I hire, how much capital shall I rent, what flow of resources shall I buy in? Okay, so that's the three things we need to take first order conditions in. d pi by dl must be naught, and it's equal to, oh yeah, and py, that's the price of the final good. What do we often do with that in macro models? We normalize it to 1. Okay, and often, possibly slightly carelessly or confusingly, we just wipe it. Because we say, oh, it's 1, you know. I'm going to do that, even though there's arguments for and against doing that. It's just notation, yeah. We just normalize it to 1 and wipe it. You can always normalize, in any economic model, basically, you can always normalize one price. Once you've normalized one price, you can't normalize any other prices. Because prices are always, the interesting thing about prices is how they are relative to each other. Okay, d pi by dl is naught equals y. So, L to the 1 minus alpha minus beta, differentiate like an economist, it's 1 minus alpha minus beta times y over L. Minus WL, okay? So then, I can put a colon here instead, and an equal sign here, right? And then I can bring this L up, and we can say WLL is 1 minus alpha minus beta y. And then, by symmetry, I can say that WKK is alpha y, and WRR is beta y. And when you add these up, what you get, y, which makes sense, pi is 0. Perfect competition. Okay. So, what's WL doing over time? WL equals some constant, I'm just going to call it C, times y, right? It's 1 minus alpha minus beta over L. So that's just constant, times y. So WL dot over WL is y dot over y. The wage grows at the overall growth rate. Of course it does. It's balanced, yeah? Production's growing at some rate, the labour force is constant, wages have to grow at that rate. Payments to capital, WKK, also must grow at the same rate, but here it's not WK that grows, it's K, isn't it? K and Y are growing at the same rate, so WK is constant. Price of capital stays the same. It's the quantity of capital that goes up. And here, what have we got? We've got WR dot over WR. So, let me do a little aside here. So we've got WR is beta, which is just constant, times Y, let me write it like this, times R to the minus 1. So then, using our simple exponent rule, and of course we could do this the long way. If you're not confident, go through it step by step with the product rule and so on. But we know from the exponent rule, WR dot over WR is just Y dot over Y. The exponent here is minus 1, so it's minus 1 times R dot over R. Okay? So if Y goes up by 1%, WR goes up by 1%. If R, the flow of the resource, goes up by 1%, WR goes down by 1%. Makes total sense, yeah? So Y dot over Y minus R dot over R. Y dot over Y is this. Well, now let's just write it. Y dot over Y minus R dot over R. And if R dot over R is theta, then we have 1 minus beta over 1 minus alpha g minus beta over 1 minus alpha theta. Sorry, R dot over R is minus theta, so minus R dot over R is theta, so this is plus theta. So we end up with Y dot we end up with WR dot over WR is 1 minus beta over 1 minus alpha g minus theta, don't we? I think. Don't quote me on that. I think that's right. So if, for instance, yeah, this makes sense. If theta equals no, g plus theta, yeah, g plus theta. So if theta equals minus g, which means the resource use is growing by rate g, then this is 0 and WR dot over WR is 0. That was the previous model. Yeah. And you might want to test if theta is near 0, that's the land model. You might want to look at what you've got for WR dot over WR. In the land model, hopefully it would be the same. Okay, final question on this part. What can we say about the initial rate of resource consumption? And I think this will be the last thing for this video. So let me just wipe this. So in the Management of Biological Resources course that some of you are doing at the same time, we actually do this more rigorously. But here I'm more waving my hands around. Okay. So what can we, what was the question? What can we say about the initial rate of resource consumption? So we've got some quantity of the resource. We can represent it by this box, okay? And then we're trying to decide how much to consume over time. Okay, so one solution would be that, yeah? We consume at this rate constantly and then we fall off the cliff. Another solution, which is what the limits to growth modelers in the 70s said is, look, this is what we're doing at the moment. When the area under here reaches this, we're going to fall off the cliff. Okay. What's the solution in the model? The solution in the model says, oh, where is it? Yeah, here. R dot over R is minus theta, which is an exponential decline. So we're told there's an exponential decline. Where should this decline start? Well, the higher we start, given the theta is fixed, yeah, the higher we start, the bigger will be the area. The lower we start, the smaller will be the area. We're going to choose R naught, so this is R, this is T. We're going to choose R naught such that this area in infinite time is equal to this, yeah. We don't want to fall off the cliff. And actually, I think in the exercises I do get you to solve this actually, don't I? I'm pretty sure there's an exercise where you get to solve this. But I'm not going to do that here. And of course, the bigger is theta, that's the steeper is the decline, the higher the initial consumption. So if theta's big, that's showing a lot of impatience. Yeah, we care a lot about consumption today, less about consumption in the future. We consume a lot of resources today, and we're going to have to cut drastically in the future. And then yeah, if the actual path, if this model is sort of true, but the actual path is like this, well then, if the model is true and we observe this, then of course that is saying that we are indeed heading for disaster. Yeah. But to get more to grips with these questions about what are we doing and what should we be doing, we need to introduce a utility function. And that's effectively what I'm going to do in the next video, which is page 6. Okay, I'm going to stop this one now.